Hi, I'm Josh, and today I want to give a quick introduction to snakeHDL, which is a new tool for creating digital logic circuits in Python. Some of the main goals of the project are to keep it simple and accessible so that anyone can just jump right in and start writing logic circuits. Uh, so what is it? Well, it has two main parts. It's an API for expressing abstract trees of Boolean logic, and I'll show you what that means in a second. And then it's also an optimizing compiler for converting these logic trees into hardware. Uh, and our compiler, it can output Verilog, VHDL, and can also create like dill pickled Python functions, which is useful for writing like automated unit tests. Um, so I just want to jump right in and show you how to use it. So we want to create a circuit, right? So we need inputs. So we'll import the API, and then so we need inputs for our circuit. So if you use the input bits function, you can create named inputs. So you specify a name and then the number of bits, and it defaults to 1 if you leave off the bits argument. So, but we want 8 bits. So we create our two inputs, A and B, and then so we've created an 8-bit named input. And what should we do with these inputs? Well, these are our options. So we'll go with exclusive OR. So all you do, bam. So what have we done now? We have exclusive OR'd the inputs A and B, but we haven't actually done that yet because BOPs, as they're called, are lazily evaluated. So when you create trees of BOPs, nothing actually happens until you compile them. And so in order to do that, we need an output for our circuit. So use the output function, and this lets you specify named outputs for your circuit. So each keyword argument that you pass the output function is an output. So then we just pass in our exclusive OR operation, and bam. So here we have it, a complete circuit. We have our inputs, and we exclusive OR them, and then we assign that result to the XOR output. Now, what do we want next? We want hardware. So in order to do that, we need to import the compilers. So we'll do Verilog. We'll say import the Verilog compiler, and then you just create an instance of the compiler. You pass in your circuit. You give it a name optionally. The name defaults to circuit. And then on the compiler, you call compile, and that returns a compiled result. And on that result, you can call save to a file path. So we'll just call it cool.v. Boom, done. And here we have it. We have our two named inputs, our two 8-bit inputs, and then we have our 8-bit output as well, which is XOR out. And then you can see it did the operation we told it to do. So that's as simple as it gets. I've prepared a few more examples just to show how it works. We'll skip the basic ones because you guys, I can tell you're ready for the real stuff. So uh, we'll show. Okay, so if you're trying to, those are the fundamental operations. But if you're trying to make like kind of bigger circuits, it gets a little bit unwieldy to keep writing the same stuff over and over again. So we also are working on adding a component library to snakeHDL. And what components are is they're basically macro functions for generating like larger circuits of arbitrary complexity. So if you want to make an adder, you just import it from the components package, and you specify how many bits in your adder. You provide your two inputs, and then you also provide like a carry in bit. For the adder, and that returns the actual result, and it also returns the carry out bit. And so we just create from that we create our output like we did before, and then we'll compile it to both Verilog and VHDL. So there you go. I'll show you guys we already looked at Verilog, so let's look at VHDL. And so what you can see here is this is where the optimizations come in our optimizing compiler. What it's doing, you see all these shared signals. It's taking it's taking logic operations that happen in multiple parts of your circuit and it's grouping them into one. So it only happens one time, and then that one performance of that operation feeds into everywhere else that it's used in your circuit. And so that lets us optimize entire subtrees out of the compilation process, and it also results in your circuit having less gates, uh, and so it makes it cheaper to produce and faster. Uh, and sweet, so those are our components. Um, the last thing I'll show is, if you're familiar with the book The Elements of Computing Systems by Nissan and Shakin, uh, in that book you start from like fundamental logic gates and you implement a full 16-bit computer. Uh, and then on top of that you build a compiler and an operating system and all that. But so what I've implemented here is the ALU from that computing platform in snakeHDL. So the ALU has two inputs, X and Y, and then it has a number of control bits that let you can preset the inputs. You can zero each input and you can negate each input, and then it also has a function selector bit, so you can select between anding and adding, and then it has one more bit for negating the output. And then here is the implementation, and it's basically just a bunch of multiplexers for selecting between the different operations, and then we have our output like we did before. And then this part just compiles it. So you can see if we compile it to VHDL, and it's done in 6 or 7 milliseconds. So it's even a 16-bit ALU. It's nice and snappy. So and there you have it. There's the VHDL for this little 16-bit toy ALU. And since we can output VHDL, we can then take the VHDL and import it into Logisim. So this is exactly what I just showed. And I've plugged a couple of random number generators into the X and Y inputs, and as you can see, it works. We can select, so when F is 0, it's anding, and when F is 1, it's adding. And we can zero the inputs, we can negate them, and yeah, so you can. It's a working ALU implemented in snakeHDL. So you can kind of see the potential that we have here. I mean, we can build the world on top of this, uh, that's pretty much all I wanted to show for this video. What time were we at? 8 minutes? Should I talk about? I'll just hint at it. So we're basically going to build the Snake PU, which is the Snake Processing Unit, and we're going to implement a Python bytecode interpreter in hardware, as like to serve as like a Python coprocessor chip, and it's going to be mega fast. So it's going to be cool. You can check out this document and let me know what you think, because it's going to be awesome. But maybe I'll save this for a later video. All right, see you guys later.